Now we're going to do something kind of fun. We're going to do diode feedback. We can put anything we want in an op-amp circuit, so why not put a diode there, and let's see what happens. And the key thing we're going to need to know about a diode is we're going to have to remember the Shockley equation that gives us the current through the diode as a function of the voltage drop across the diode, where IS, M are constants related to the diode, and the VT is the thermal temperature. It's basically kBT over E, so it's the room temperature energy divided by the electron charge, and there's that -1 there. And this really is that -1 for all practical purposes doesn't matter. It's IS E to the VD over MVT. So that gives us the current through the diode as a function of the voltage. It would also be useful to invert that, and if we can do that, the diode voltage is going to be MVT natural log of I diode over IS. So there's the two relevant equations here. Here's the diode circuit, and let's look at that a little bit. We've got to analyze this. There's definitely negative feedback. We're connecting the output to the inverting input. That means that V minus will be locked to V plus, and V plus is 0. So V minus will be at 0 volts. So we have a voltage drop here. The current flowing into this, IN, is going to be Vn minus 0, the voltage drop across that resistor, divided by R, or just going to be Vn over R. And no current flows into the op-amp, so all that current must flow through the diode. So that has to be equal to I diode. All the current has to go through the diode. So there's a voltage drop across the diode given by this expression here. So the output voltage, V out, is going to be 0 volts minus V diode. The 0 volts here minus the drop across there. So that is going to be minus MVT natural log of I diode for IS. And that's going to be V out is minus MVT natural log Vn over ISR, or MVT log Vn plus MVT log. So the interesting thing here is this piece here is all constants, and the output voltage is proportional to the log of the input voltage. So what we have is a logarithmic amplifier. The output is proportional to the log of the input voltage. So if we have input voltages that vary over wide orders of magnitude, this circuit will have an output voltage goes like the log of that, so it'll vary over a much smaller range of output. So if you have a circuit that needs to be sensitive to 10 to the minus 3 up to 10 to the 3 or something, or has ranges there, you may want to take the log. So this is actually very useful for big ranges in input if you want to look at the output over a very finite range. So cute little thing, you put a diode in as feedback, you get an amplifier whose output is proportional to the log of the input voltage. We could do something different as well. You can well imagine, well, I put the diode here and the resistor here. What would happen if I flipped them? And usually when we wind up flipping those two components, we get the inverse equation. And the inverse of a log is an exponential. So you would expect that the output voltage may well be proportional to the exponential of the input voltage. And we can see that. Let's just flip that here. We'll put our diode here. Resistor, diode, V in, V out. And I'll just remind us that the Shockley equation, the voltage drop across a diode, MVT, natural log of I diode over IS, or the current through the diode is going to be IS e to the V diode over MVT. So those two equations there. Let's now look at this. We have negative feedback, so V minus will be V plus, and V plus is locked to ground, so that's going to be 0 volts. So the voltage drop across the diode, it goes from V in to 0. So V diode is going to be the input voltage. We know the voltage drop across the diode. Given that, we can calculate the current through the diode. So I diode is going to be IS e to the Vn over MVT. There we're seeing the exponential of the input voltage. And we also now know that all of that current has to flow through the feedback resistor. So V out will be 0 volts, voltage here, minus the voltage drop across the resistor, I diode times R, which is going to give us V out will be minus ISR e to the V in over MVT. So we have an output voltage that's proportional to the exponential of the input voltage. So we have an amplifier that if we have a very, very tiny range of input voltages and we want to spread them out, we can use the exponential to expand the scale. Opposite, if we have a very, very wide range of input and we want to compress them, we can use the logarithmic amplifier to compress them.